So my name's Richard. I'm a building performance consultant at Mesh and the team lead for um, resi and non-resi novel projects. So some projects that are a little bit more out of the ordinary. And I put this CPD together as a result of recent project work we've been doing, and emerging policy. So what I'm going to do is um, take you through what whole life carbon is. I'll introduce you to the RIC structure, how it's calculated, and then how this relates to the what is now known as the Low Energy Transformation Initiative, or LETI. And then we'll touch on building circularity, some design tips for reducing whole life carbon, but I think more importantly, changing and emerging policy in this area, um, which I think will be really quite interesting. And then we'll go through a case study for a project that was completed not too long ago, and we'll sum up with some key takeaways and any questions you might have. So, whole life carbon is all about identifying the overall carbon emitted from the construction materials that make up the project, but also the operational carbon. So operational emissions we'll be familiar with as a result of Part L compliance calculations, for example. And what we're doing, we're calculating these emissions based on the day-to-day running of the building over its entire life. There's quite an encompassing. Um, the Royal Institute of Chartered Surveyors first published in 2017 a structural approach, and the purpose of this really is to avoid focusing on operational emissions alone. And it really is an effective path to a lower carbon future that goes beyond just thinking about the performance of the building um, from a thermal point of view, or energy, or occupant comfort. So it's just adding another dimension that have long lasting ramifications really. And most importantly, it's consistent and it's comprehensive. And it can be quite detailed, especially if you're working on non-domestic projects in the context of BREEAM. So captured within the RIC structure, and when we're looking at whole life carbon, we're talking about everything from demolition and facilitating works if you've got a brownfield site. We're examining the carbon in the substructure, the superstructure, so the framework, the finishes, the FF&E, building services, any prefabrication, works to existing buildings, and we can also examine external works as well, such as landscape, hard surfaces, and so on and so forth. So what RICS did was create a structure based around 4 modules, and basically it's looking at the cradle to gate creation of products. So that's everything from extracting and supplying of raw materials and turning it into a product. And then we get an extension of that, which is cradle to practical completion, which is basically about transporting those products from a factory to a site and assembling them into the finished product. And then we have cradle to grave. This includes use and end of life. So we're talking about repair, maintenance, refurbishment, as well as replacement of any materials, um, such as building services, for example. Building services plant has limited lifespans, and it may be replaced 2 or 3 times throughout the lifespan of a building. And then we get to cradle to grave, which includes the end of life stage. So, say, for example, designing for deconstruction, uh, considering waste processing and disposal. And then we get cradle to cradle, which is where we look at the benefits beyond the life cycle of the building. So, are there materials that can be deconstructed and repurposed? That could be repurposing as the material they are, or it could be downcycling. um, or it could be used for energy production. And so these are the modules that it's broken down into, and we're talking the units of measure are all based on the weight of CO2 emissions, um, but they also can be normalized into per meter squared, by volume, or regarding distance or energy consumption as well, or even in the case of something like a data center, then in terms of the amount of compute. So start talking in terms of megabits per second. So module A in a bit more detail is the extraction and supply of raw material and its transport to site. And the thing to look for these days is really as to whether the products that you're specifying have an environmental product declaration. And what that is a third party assessment as to the global warming potential of the materials and products you're prepared to use for your project. And while this is not so important in, say, domestic projects, unless the clients are particularly aspirational, it is certainly part of the BREEAM structure if you're pursuing um, credits surrounding material use and reducing your embodied carbon that way. There are a number of default specifications that can be used as part of these at this stage to sort of determine which products are going to be used. So, for example, we've got C32 to 40 concrete with 20% cement replacement. Now, and also we've got recycled content for steelwork, whether structural timber should be FSC, which typically it is these days. And then we've got recycled content in aluminium and plasterboard. And what's important to remember is that at the early design stages, so we're talking early stage 2 is when we start quantifying the quantities of materials and the effectiveness of the choices, is that the calculator we use have a very extensive database of material specifications. So, for example, we can look at um, different recycled content amounts in steel, for example, and the Institute of Structural Engineers specifications for different concretes with different aggregates, percentage of aggregate mix are all available to us to start to really get under the skin of how much embodied carbon there is at A1 to A3. Then we have the second part of Module A, and this is all about transport to site and construction and installation. So, if you're familiar with some of the more sort of bioregional analysis or approaches to sustainable construction, then the locality of the suppliers for materials can be equally as important because there are transport emissions associated with the construction site. So a product that's coming say 200 miles away is going to have a higher embodied carbon than sourcing materials within a 35-mile radius, for example. And then we have construction and installation as well. And this is a little bit of a grey area. It can be tracked at stage 5, but there are some generic allowances for different regions in Europe to account for construction emissions based on the site area. So if we know what the limits of the site are, this is something that we can take into account quite easily. The one thing I should mention about the transport to site is the reason that is important is that we have projects that use cross-laminated timber. Now, at the moment, this is a material that's not widely available in the UK as a native material. And often than not, it comes from the Alps or Finland. And so there is sea transport involved as well as road transport. So some of these transportation distances can actually become hundreds or even thousands of miles if we're um, really looking at this in a very accurate manner. Then we get to Module B. And this is all about building in use. So post-completion, um, we're looking at taking into account maintenance and repair and cleaning, replacement of building components. So it's important to understand the life cycle of external glazing systems, for example, the types of doors you might be specifying. And for us as building service engineers, it's important to understand the replacement life cycle of solar panels because, you know, building services plant can vary in its life cycle between 15 and 25 years. So it means that some elements of the energy strategy, as it were, might be replaced 3 or 4 times during a 60-year lifespan of a building. And then also we've got in there allowances for refurbishment activities. So it can be refurbishing elements of the external or internal finishes, and also refurbishment of doors, replacement of windows, and so on and so forth. And then alongside this, we've got the operational energy use. Now, what's becoming more important is this includes the regulated and unregulated energy use, as well as on-site energy generation. And you'll probably be familiar, if you're familiar with LETI, you'll be familiar with the term energy use intensity, which is where we're taking all these sort of energy uses and breaking it down into kilowatt hours per meter squared per year. And there are a number of approaches to that, but more typically it's CBDM TM54, which starts to look at small power loads, could be catering. If it's offices, it's looking at the IT infrastructure and the energy draw on that. And so it becomes quite a detailed exercise to understand them. And this is something we do on a regular basis. And then we have operational water use as well. And this is based on approved document G water calculations, because electricity is used in the production of potable tap water. So it's important to understand the volumes of water that are being consumed by a project each year as well. B4 is specifically about refurbishment or replacement. And so, this is what I meant about similar to building services technology. Typically the lifespan of a roof is 30 years. So it's going to get, based on examining a 60-year lifespan of a building, then the roof will be replaced at least once. Your superstructure could be the same. The finishes or certain substrates and the finishes could happen at least once a decade. And the same for FF&E as well. And like I said earlier, fixed plant can be replaced every 20 years. If it's something like a fan coil unit for tempering air in a space, then that might be every 15 years. And that's the same as lighting and communications infrastructure. But sanitary ware and transport and water disposal systems they're a bit more hardy, so they don't need to be replaced so often. And then we're looking at the facade, then we're anticipating significant replacement of elements of the facade, depending on what's specified for resilience and durability, but that could be every 30 to 35 years. Then we get into module C, which is the end of life. And this is really, if you're familiar with BREEAM projects, this is where we're sort of designing for end of life and deconstruction and demolition, and start to quantify the transport costs in terms of carbon to disposal facilities, and it includes waste processing and actual disposal of the material. And we can actually look at that in quite detail, and actually take a look at the design stages to how that material might be processed. So, for example, masonry elements are typically given over to an end of life where they're crushed down and used as hardcore, for example. If it's a solid brick building, on simple terms, then it's possible to run calculations that assume that, say, 45% of the brick will be reused in another building, and therefore it changes the weight of the embodied carbon of that material. So only sort of 55% would be crushed down and used for hardcore. Um, and then the same with timber products. They are generally assumed to be incinerated. Now, if you've built, if you're demolishing or deconstructing a CLT constructed building, so it's cross-laminated timber, is to ask the question of what area of that material can we actually cut down to a smaller size and reuse it for another project elsewhere. So it's all about not just about thinking up to the point of completion, but it's really thinking from day one about the entire life of the building. And then we get module D, and this is really about looking at the benefits beyond the building life cycle. So this is all about reuse, recovery, and recycling potential of materials. And it's really there to give a broader picture of the environmental impacts of a project by accounting for future use of various components of the building. So, for example, if you're building a timber building, then in the early stages, so A1 to A5, that material has already sequestered carbon. And although that is a negative number, it is not subtracted from the project that it's being used for. If it is successfully deconstructed and reused on another project after the end of life of the current project, for example, then that carbon benefit gets passed on to the module A of the next building, and therefore you can start subtracting sequestered carbon. And why that's important, I'll demonstrate that a little bit further on in the case study. So how do we calculate whole life carbon? Well, the first thing that is generally recognized in the industry that it has to be impact compliant. And an impact compliant tool is basically equipped to deal with life cycle assessment, life cycle costing, and it uses the interaction between 3D CAD and BIM, dynamic thermal modeling, and it is BRE compliant. And this was put together a few years ago now, and it's something that's just gone from strength to strength. And it's got uses in BREEAM, corporate social responsibility assessments, full life cycle assessments, and also the cost benefit analysis of design options as well. Because obviously, if you're trying to make your building, say, for example, more organic to bring down its embodied carbon, then that will start to impact the cost plan as well. So, you have to start looking at all the different factors associated with producing a building collaboratively. You can't just make a change of one aspect of the building and then allow the knock-on effect to sort of ricochet through the design team and try and solve the problem that way. So the way we work at Mesh is that we use a platform called the IES virtual environment. We use that to build full dynamic thermal models. And we can use that for a number of reasons. It can be used for heat loss calculations, overheating, understanding indoor air quality, looking at passive design. But what it does enable us to do is interface with a globally recognized platform called One-Click LCA. And it's this combination that can provide evidence for up to over at least 75% of the BREEAM excellent credits, and that fall within project management, the health and well-being of occupants, the energy strategy, water, the impact of materials and reducing waste, but also testing projects for resilience and durability under future climate scenarios as well. But we apply this to all our projects, regardless of type, scale, or BREEAM schemes. And as to how we present this, Well, since Letty went from being the London Energy Transformation Initiative to the Low Energy Transformation Initiative, it's become a really robust um, way of presenting the outcomes. And it also aligns with the REBA 2030 sustainable outcomes. And so it enables us to benchmark and compare designs in a robust and constant manner. But Letty asked for particular things to be considered. So it considers modules A to C at the moment, but it excludes operational energy and operational energy associated with water usage. But what it's doing is it's seeking at least a 60% reduction in embodied carbon for domestic offices and education. And it's also asking for energy use intensity to be um, below 35 to 55 kilowatt hours per meter square per year, depending on um, the type of project. So, for example, it's allowing 30 kilowatt hours per meter square per year for unregulated loads for offices and education. Sorry, 40 kilowatt hours per meter square per year. And also they're asking for 50% of material to be reused. Um, so, so that sort of replacing virgin material with reused material, but also designing for disassembly or reuse so that 80% of the material is reusable. And these are really ambitious, these are great aspirations, and they're really ambitious, but it can be done. I think that's really important. So how do we lower whole life carbon? Well, it's a bit of a cat's cradle. I mean, imagine each finger is a variable in the design, and they're all linked by a thread. That when you pull on one aspect of the design, it's bound to have a knock-on effect on some other aspect of the design. So really, there are some classic considerations to be had. So can we make use of orientation and form factor? And that's really to gain from passive solar heat, but also reduce the energy loss of the building as well. So that's really the first phase in sort of balancing the energy budget. And then the question is, fabric first, is refurbishment better? Or are there historical and aesthetic factors of concern, or even structural safety or health and well-being, as we've seen recently in some of our projects? And can the superstructure be reduced or at least designed for deconstruction and reuse elsewhere? So really the key is, do we build wisely and efficiently for longevity? Do we build more organically? Um, and that's quite an interesting concept, because there are, most common materials we'll hear about are polyurethane or PIR insulation, for example. We'll hear about mineral wool. Um, but equally, in terms of thermal performance, when you're looking at mineral wool, then wood fiber insulation and hemp insulation have very similar thermal performance. And therefore, you can actually substitute these materials and start to reduce your global warming potential of your building. And then the question of how do we build for resilience? Is it better to build more organically with our external finishes and replace them more often and reuse or recycle that timber, for example? Or do we pay a higher global warming potential price by using masonry, um, which has that higher global warming potential, but equally, can you source masonry finishes that are recycled from the end of life of other projects? And then, of course, how do we design for end of life, and how do we collaborate on this? And it's all these factors that that contribute towards lowering whole life carbon. What we're now seeing is a change in policy, um, and we're seeing climate emergency declarations being made by local government. Um, for various reasons. Some of it is partly political, some of it is because it's felt that central government is not doing enough, and therefore more local action is being taken to um, you know, encourage a more sustainable built environment. So we're seeing policies emerging that have different methodologies but have the same aim, and they're generally supportive of retrofit to reduce whole life carbon, but the calculations are being done in combination with SAP calculations. And of course, the new Part L's SAP 10.2 calculations are now a lot more stringent than they were a couple of years ago. But at the same time, these climate emergency declarations and these policies are there to support more sustainable new build. So if you're making a case whereby an existing building it's not feasible or to actually do retrofit, then it's at least encouraging a highly sustainable alternative. And so we get into whole life carbon again. But as we know, some of you might have experienced this, the difference between design and reality. I mean, SAP is not as realistic as one might hope, and it's not as accurate as the dynamic modeling of energy use intensity if you're using dynamic thermal modeling software. So we've got a couple of emerging policies or methodologies, and there are variations on this, and it probably will normalize over time once the evidence base builds up, and then it gets revisited. So really, the first one is looking at the target emission rate, the number of panels and the watts per panel, and then understanding on a very simple level the annual CO2 savings that can be done. So this is kind of almost a very light approach to undertaking a feasibility study on renewable energy. This particular calculator is a little bit more tricky because what it's doing is asking us to calculate the embodied carbon of an existing building, and then the amount of upfront embodied carbon in the proposed replacement building. When we say upfront embodied carbon, that's the module A consideration. So that's the raw material right through to creating the products and assembling it on site. And then looking at the amount of carbon through reuse or recycling from the existing structure. So then we end up with a net carbon cost of the project in tons of CO2. Then what it's asking for is to calculate using SAP the TER and DER, and then what that does is provide the annual savings of CO2. And it's in this particular example, the savings would be 2.1 tons of CO2 per annum for the entire gross internal floor area. And then what the calculation then does is divide that net total carbon cost of the project, so this one here, by that annual saving. And it determines the number of years at which the carbon would be offset. And what this policy is asking for, certainly down in the West Country, is that the offset will be completed within a maximum of 25 years. Now, this is obviously really quite difficult to achieve. It does get questioned, but it's not the be all and end all. And the point of the policy, as I was saying, is really to encourage more sustainable design thinking about the choice of materials and the energy use intensity, and then we can work out what this is. And of course, we're starting to also look at this in reverse, so we can understand we can complete the SAP calculation for the proposed design and understand the existing embodied carbon, and how much could be reused, and then it helps us set a target for the upfront embodied carbon for the proposed design to meet that 25-year limit. Now, the 25 years does sound like a short period. It does align generally with the idea of being net zero by 2050. Conversations we've had recently, we understand that actually some people were proposing that that limit should be 10 years. So it meant that it was becoming almost nigh on impossible. It could almost stop new construction in its tracks, but it really strongly supported the policy of completing retrofit and refurbishment. So this is an example of where we're sort of playing around with the working this calculation in reverse. So, for example, we know it's just a mock-up, but if we've got a sort of 40 for sort of run about 45% reduction in energy use, and we know the embodied carbon and how we can determine from the analysis of the existing structure how much material can be reused or recycled. Then we can use it to say, right, the limit of your upfront embodied carbon in your replacement building is X. And so part of our design process is then to model the proposed design and start to do, if you want, stress analysis on the choice of materials that are actually included in the design and look at alternative materials that might bring down that global warming potential. And then we can start to refine the design to reduce that upfront embodied carbon, and with the aim of meeting that 25-year limit. So just by way of a case study, and it's really, this particular case is about this project want to double the internal floor area of a 100-year-old property. And the design team were anticipating when the planning application goes in that there are questions that are similar in nature to the calculator we just looked at about reducing whole life carbon and whether retrofit is actually better. So we started off by looking at this project and saying, well, what if all three options were constructed as new today, but retained their existing energy strategy? So as you can see, the existing house, it's a solid masonry construction, very traditional, built around about 1907, and it's on an oil system. So the regulated energy from the space heating is huge from the carbon emissions of that oil. So then what we also compared it to was, okay, what if we have a look at the fabric of the building and have a look at reasonable consequential improvements so we could improve the fabric first and start to bring down that peak in annual energy demand, and what would happen if we then put that house on a ground source heat pump. And then, of course, we've got, you can't see it, but there is actually a slight increase in the A1 to A3 materials. And that was mainly to do with lining with a composite PIR plasterboard system that would improve the U values of the property. And then we compared that with a more organic passive house standard new build, which would be on ground source heat pump and have a element of PV on it. So because there's new materials, you can see there's a much greater transport contribution. And of course, it's ever so slight, but there's an increase in the contribution from on-site activity as well with all the new construction work. But then start to think about, well, what about your question about that that existing house already has modular embodied carbon? So we removed the materials. They're already there. There's not a new upfront embodied carbon. It's pre-existing. And so when we compared that with the improved existing house, there are materials in here, but because it's been reduced to just being the insulation option, then it barely shows up at all. And then we see that there's a much great. It reduces the whole life carbon of the improved existing house. It makes it sort of more on par with the proposed design. Um, I mean, this is actually not including any stage D external impact. So there's no materials taken from the existing house and used as a contribution to the proposed design. And so, the question is, does it make the argument for demolition and new build weak? How, when it's this close, is there justification for refusal? And so there's a risk there. And that's especially if the um, the existing embodied carbon costs or the embodied carbon cost of the existing house is added to the proposed design. And therefore, the improved existing house is proven to be a better option. But when we started to look at that in a bit more detail, the argument the argument arose that actually, well, the reason this work was being the proposed design wanted to be taken forward is that the gross internal floor area wasn't sufficient for their needs, and therefore, if we were to present a balanced case for improving the existing house and compare it for a like fit for purpose internal floor area with the proposed design, then we should account for that additional floor area with on top of the improved existing house. So you can see from the breakdown of the figures, we've got no material accounting for the existing house. So, like I said, all the materials are on site, but the improved existing, this now includes the materials required to bring the existing fabric up to standard, but it also includes the material requirements of increasing the gross internal floor area. So it started to push that figure up slightly. And then we've got the proposed design, which is basically the upfront carbon for the proposed design plus the quantity for the existing house. And that brings us to that figure. Now, that's all really well and good. And this is where the discussions around the use of SAP started to creep in as well, because when we're doing our thermal modeling, we're effectively doing a CBDM 54 analysis on regulated and unregulated loads. So we understood that the operational energy of the existing house is going to be about just over 2,000 tons for the next 60 years. If we improved the existing house, but at the same time made it larger, then we were looking at a 50% reduction in operational energy over 60 years. But if we were to demolish and rebuild with a super insulated passive house standard, very airtight building fabric, then we could reduce that operational by 75%. But of course, with the increase in floor area, then there's likely to be an increase in potable water consumption. And then there are sort of waste transport figures associated with demolition and waste processing. And then we have waste disposal. But what was really important is this figure down here. So without really making too much effort to have a look at the existing house materials, based on the type of materials used in the construction, the end of life benefits are actually around about 47 tons. So, and this is the, when I was talking earlier, this is the carbon that gets paid onto the next project. So it's almost a biogenic or sequestered carbon or reused carbon that comes out of the existing house and can be subtracted from the proposed design. So we get to pass on that carbon benefit. So we end up with a picture more like this. So we ended up with the existing house that's unchanged. We've got a lot more waste processing for the improved existing house with the new extensions. So the amount of A1 to A5 material and activity actually increases. But then when we're looking at the proposed design was still including all the original material, but we were actually able to subtract that 47 tons of deconstructed material, and that could be taken on to incineration for energy generation, crushed down for hardcore on road building or foundations, and so on and so forth. So what it meant was, we could improve the existing fabric um, with the additional and also enlarge the house, but it would still be underperforming when compared with the proposed design. So this was a much stronger argument for um, demolition and rebuild. And then what we were able to do is take the detailed number crunching and input it into the Leti presentation. So we've got two sets of information here. Well, the top one is really the outputs from the one-click, well, the high-level outputs from the one-click LCA platform, which gives us an indication of where the material carbon transport, replacement, and waste processing, where the embodied carbon resides by element. So this is, again, just to recap, this is a solid brick 100-year-old property. It's got minimal technology. It's an oil-fired boiler with radiators, and so most of the materials are sort of taken up in the external walls, internal floors, roof, and so on and so forth. But we were able to take the whole life values and plug them into the Leti calculator, which gave us this output. So we understand that even by today's standards, the um, the house would be performing really rather well. So you could, it's still in a good place even for a property of its age. But then once we started looking at improving the existing building, then and enlarging it, then the rating of it fell because we've got some, like I said, higher GWP materials in there. There's more material in there that's not necessarily um, beneficial for the environment, so it's got a higher GWP. And also with the enlargement, then it started to push up the life cycle embodied carbon as well. When we compare that alongside um, the proposed design, you can see the sudden shift into building technology. So in here, we've got ground source heat pumps with horizontal collectors. There's a reasonable size solar array. It's not overly massive. It's probably twice the size of a typical detached house array, so about 8 kilowatts. But then we've got because it's a more organic construction, though it's made predominantly timber frame, wood fiber insulation, then that starts to reduce the embodied carbon of the structure, and so it leaves room for designing for resilience, or bringing external masonry elements in, and making the fabric more resilient in the face of climate change. So, what are building circularity? It's interesting it's always interesting to know that 13% of materials in the UK are simply discarded. So landfill, incineration, that go to no use whatsoever. So when you start hearing about building circularity, the idea is to move from extracting raw material and then just discarding it. So moving away from a extract and throw away culture to one that starts to minimize the use of raw material and looks to retain and reuse at module D. And so there's a couple of really good links. It's worth looking up the Ellen MacArthur Foundation, the global leaders really now on building for a circular economy. And of course, there's the circular economy statement that is now built into the new London plan. So how much of an existing property could be reused on site? And this is a question really to ask yourselves when you're starting to design buildings. Is it 90% of the existing roof tiles? Is it 50% of the brick? Is it all of the timber? How can we make these what we're doing better for the environment, and really reduce the use of raw materials? So with this particular project, started looking at whether we could reduce module C and increase module D. So, as a result of the materials that are going into this project, and this is all coming out of the one-click platform that we use, we know that, all the brick and timber would be 85% virgin material. And at the end of life, if we were to do business as usual and not, not recycle, then 80% of that material is going to get downcycled or simply incinerated. So we started looking at the end of life of the materials and questioning about what we could do with them. And then when we're doing these calculations, it was a case of going through each material in turn and saying, right, we have timber sheathing. Are we just going to incinerate it, or can it be dismantled and reused again as timber sheathing? Now, whether that is used for sheathing again or doing used for casting concrete in a limited manner, it all has a repurposing use. And it was the same with the brick as well. If we could take 50% of the existing house brick that form the solid masonry walls and use that as the external facade, then we start to make huge savings. So we started to get reuse. We've switched reuse of material from 0 to 68% just by thinking at an early design stage about how materials might be used in 60 years' time. So you have to sort of it's a bit of a leap of imagination really to think, okay, the world in 60 years' time, what's it going to need and how is it going to use it? So it's all now part of the design process really, and part of our design thinking to actually question this and actually start to think about it. And so we ended up with an outcome. So the current average design is LETI band E, and this relates to the REBA sustainable outcomes. This has all been harmonized over the last year or two. And so the REBA 2030 target is LETI band B. So because of the simplicity of the existing house, it actually achieved the LETI band B, even though it was grossly inefficient from an energy point of view. Now, by improving the existing house, we knew that the upfront and the life cycle embodied carbon would actually increase. And so it actually became a worse LETI band. But by really examining more closely, the limited use of masonry and going for a timber frame construction with wood fiber insulation and minimizing the raw materials or process materials, then we would start to get in. We could have a project that would be LETI band A plus. I mean, this is really, almost as good as it gets. I mean, it's a fantastic outcome. So takeaways from all this. It's no longer just about Part L. It's no longer really just about getting that compliance, producing the energy strategy, and moving to renewables, or even just thinking about occupant health and well-being in terms of overheating and daylight. But it's about the whole life of the building. We know, there is an established structure and there's a measured approach. So it means that from project to project, we know that regardless of the outcome, the methodology is consistent. And it is a policy that is spreading. So we've got projects where it is policy. We have projects where policy is likely to be written off the back of the reports that we are producing. And at the same time, we've got design teams preempting awkward questions and the potential for this policy to become more real in the areas in which they're working. Sequestered carbon always gets passed on to the next project. Unfortunately, it's never part of your project, but that's just the way it is. And the Institute of Structural Engineers and RICS, etc., all agree on this. The process is integrated with energy and water calculations, but also understanding occupant health and well-being, because all this analysis is done through dynamic thermal modeling and the BIM integration with one-click LCA. And collaboration, as always, is everything in presenting accurate outcomes. So we're finding that is much it's a far more collaborative process. It's the only way I can describe it. We can have a starting point with a proposed sort of set of drawings or some sketches and some ideas about construction, but ultimately the earlier in the design process that we collaborate on this and start to examine all the options, then the better outcome the project will have at the end of the day. And we're designing for end of building life, not end of material life. So we're aiming to make our buildings fit for purpose, beautifully and comfortable to inhabit, but at the end of the day, they need to be able to have effectively an afterlife to them, I suppose. Oh, I've got a repeat. Oh, and that was the thing. It was all about these policies that are spreading are going to seek to prioritize retrofit and reuse, or if that is not an option for various other reasons, whether it's structural, health, or material degradation, then it's about posing a much more sustainable new build that proves that the policy can be met and supporting the planning applications. And really, that brings us to the end. It did take me as long as I thought.
No, thank you, Richard. Marvelous there. So, well, it's so much detail there, and that case studies help bring it to life, because we've had previous sessions on whole life carbon, but this session here has really put sort of meat on the bone. So thank you for taking the time to put this presentation together. If anyone has any questions I've asked on chat, please do so. We've got time for one or two. Just while I'm waiting for a couple of questions, again, Richard's presentation is quite timely, because in a couple of weeks we've got Charlie Luxton talking about circularity, and he's always really, really interesting. So it'd be good to do that. So yeah, please register for the one on the 13th, I think it is. In the meantime, so we've got the regulations, but where's the change being, or where's the change being driven? Because obviously you've got the homeowner, or you've got the and the developer and the architect. So in order for, I mean, how many does John homeowner know about this? Like who's advising on what needs to be done to make these changes?
We're seeing the changes being made on a local planning policy level. So whether they're being written into the local plan. And we have projects that have, were submitted a couple of weeks after the policy was written into the local plan, and of course now they're having to revisit the designs and put it in the correct context. So it's quite interesting. And like I was saying, we've got other projects where this is not yet policy, but the planning officers have had this discussion with the architects and the developers in meetings. So they're looking to understand whole life carbon and how it's calculated and what the various implications are, and then it will start to become local policy as well. So in the meantime, we have to work with this method and using SAP, because I think SAP is used mainly because it's accessible, and the effort that goes into dynamic thermal modeling is far greater in terms of time than doing a SAP assessment. So it's that level of accessibility. It's a bit like the simplified and the dynamic approach to overheating. So it will then mean that people start to understand whole life carbon, certainly from a planning policy point of view, and it will be reinforced that way.
Cheers, Richard. And we don't often have anyone from, well, beyond Doug. It's been a while since we've heard from you, Richard, so thanks for that. But I suppose bit of a plug then in terms of who well, this is such an unoriginal question, but in terms of where can people find the help in order to undertake this work, apart from Mesh Energy or along with Mesh Energy?
So if you want to understand it in more detail, the Royal Institute of Chartered Surveyors publish guidance on it. And that gives a really good breakdown of all the different modules and what is included in the modules. It's fairly accessible. It's not written in a technical manner. It's all written in a narrative / explanatory manner. So it is accessible. So that's the best way to understand it. And it's still a relatively new field. I mean, because we're finding that there are, although the idea of impact analysis and whole life carbon has been around for at least 10 years now, the approach to how the numbers are understood and the justifications made for a project do still seem to vary at the moment. So while down in the West Country, they've set this 25-year target, and it is purely based on the carbon cost and the TER and DER. Then in the south, further over to the middle south of England, we've got projects where they want to understand the whole life carbon and the operational energy. So there are different schools of thought in different regions about how this should be approached. But ultimately, it's designed to either encourage retrofit and refurbishment of existing assets, which had a lot of support through the architects, the AJ, the retrofit one. It's also had a lot of publicity off the back of Oxford Street and Marks and Spencer's. And so, but at the same time, it's not to just view this emerging policy as something that only encourages retrofit. It's always there. It's also there to say, look, the flip side of this is if you can design a really sustainable low GWP building, then that is equally as good. We need to present the whole picture and create a robust argument, really.
Cool, makes sense. No, well, I think that's bang on the hour. So yeah,
Okay.
thanks for the time, Richard. Thanks everyone for attending. As I said, I'll upload the recording. Richard will share the presentation with me, and I'll add that to the upload as well. So enjoy your.
I think if anything, if there's any significant change in the next 6 months, then I think we'll be doing an updated sort of repeat of this session just to keep everyone up to date, really.
Yeah, no, it's been very helpful. Thank you very much. Cool. Okay then, guys. Thanks a lot.
Thanks. Have a good afternoon.
Cheers, Ed. Bye.